In this optimization problem, we are going to try to find the radius and height of a cylindrical cone, soda can, with a volume of 355 cubic centimeters, which is a 12-ounce soda can that minimizes the surface area, right? So the shape that we have for all of these soda cans, are they really the best? Are they giving you the minimum amount of surface area with a set amount of volume? Right? So you're making an aluminum can, are you putting in the least amount of material to make it? So let's find out. So what are dimensions going to be? So first thing is we need to figure out what it is that we're trying to maximize or minimize. And we are looking to minimize surface area. Minimize surface area. So we need some sort of a surface area equation. Let's draw our picture of some sort of a cylinder. And we have a radius and we have a height. So to find surface area on this, we have two pieces that make this up, well, three pieces. We have top and a bottom that match. Right? We have two of these. And so to find the area of the top and the area of the bottom, those are just circles. So we have pi r squared, but we have two of them. 2 pi r squared. And then if you were to unroll the horizontal part of a cylinder, you're getting a rectangle. And to make that, you're talking about the circumference. So 2 pi r and the height. So 2 pi r h. R h is what we got. So right now we're going to be doing the derivative. Well, not right now, but eventually we're going to be doing the derivative. And we're going to have a problem when we're going to be doing the derivative with respect to two different variables here. So it would be wonderful if we could sub out ideally this h and put everything in terms of r. That's where the volume comes in. We have a volume of a cylinder that's set, and I bet we're going to be able to sub it out and find something related to the height. So our volume formula for a cylinder is the area of the base times the height. And the area of the base is a circle, so pi r squared times height. And so what we know is we have a 355 cubic centimeter volume. And we have this formula of pi r squared h. We could isolate h very nicely just by dividing this over. So our h value is going to be 355 divided by our pi r squared equals h. Wonderful. We can sub that in, and then we can do our derivative. So our surface area is 2 pi r squared plus 2 pi r times 355 over pi r squared. All right, so one last thing is typically when you do some sort of a substitution, it's always nice to do some sort of a cleanup to make it a little easier to do your derivative. And so we have the pi's are going to go away. They cancel each other. One of those r's can cancel one of those r's. So we're really looking at 2 pi r squared plus 2 times 355. It's going to be 710. And then actually, this is going to be over r. But since I'm going to do a derivative on that, I might as well go ahead and bring the r up and make it a -1 so we do the derivative. We can avoid the chain rule. All right, so let's do our derivative of our surface area. And we're looking at 4 pi r minus 710 r to the negative, that's not r to the -2. All right, so if we kind of rewrite all that, we set it equal to 0, we're looking at a 4 pi r minus 710 over r squared set equal to 0. And that is going to be a calculator kind of a thing. So we are going to use a calculator to solve that. And so to solve it, we are going to graph it. We're going to graph it and find out where the x-intercepts are. So let's jump into the Calc then. So let's clear out, and we're going to do 4 pi x minus 710 over x squared. And then let's go ahead and graph it and see what kind of x-intercepts we have going on. Perfect. So we have some sort of a value right there. So let's go ahead and figure out where that is. Our x-intercept is, let's see, we're in the negative values, getting up closer. So we're on the left side. I don't know if it's showing up or not. Cool. So there's a left side, there's a right side, get an answer. So we are looking at an R value of 3.837 centimeters. And then how would we know for sure that that is going to give us a minimum? Is we would take that critical value, 3.837, and we would be plugging in values to the left and to the right of that derivative. And so we can actually just utilize what we have right here is we have negative y values on the left, and we have positive y values on the right, which represent negative slopes, positive slopes of whatever this original equation is. And so we have a negative transitioning to a positive. So we know for sure that we're going to have some sort of a minimum. All right, so what is our minimum surface area? That's what we're looking to find out. So our minimum surface area, that's going to be us taking this and plugging it into our surface area equation. All right, so I can just plug it right into that piece right there because it just has the R. I don't actually have to find the height associated to it. I could, let's see, we do. So our height is us taking this and plugging it into this equation right here. And if we plugged it into that equation, we would get 7.675 centimeters. I don't know why I put a cube on that. All right, so our minimum surface area is now if I take those values and plug it into this equation and figure out our surface area, our minimum surface area would be 277.55 square centimeters. So that's the least amount of material, the least amount of aluminum that they could use to make a soda can, given that it has to be a cylinder with that set volume associated to it. So if you actually do a soda can, so there's our answer. But the actual soda can does have a radius of 3.25 centimeters. And so if you have that one, it's a little bit, so this one would be a little bit wider and a little bit shorter than a real soda can. Soda can's a little bit narrower, which makes it a little bit longer, which gives you a surface area of about 284.83 centimeters, square centimeters, which is about 2.6% more. So pretty close. I'm assuming that they make it a little narrower so it fits the hand a little bit better. Because otherwise, if you look at this, it might be a little bit too wide and a little bit too short. So kind of your hand ends up being wider in order to grab it. So maybe there's something to that dimension that's a little bit nicer, and it's not crazy more, but it is a little bit more. So making it a little bit wider and a little bit shorter would give us our minimum surface area based on that volume.